Welcome to the UT Energy Symposium. Our speaker next week is going to be Dr. Mark Tepper, who is the Associate Director of the Program on Energy and Sustainable Development at Stanford University. Mark is going to talk about national oil companies fueling anxiety. And it's actually based on a recent book that Mark co-edited, and I was a contributing author to that book. And this essentially talks about national oil companies' relationship with their governments and what it all means for world energy supply. It's going to be a terrific talk. Please join us next week. So with that, it's a great pleasure to introduce our speaker today, Dr. Jay Apt. Jay is a phenomenal guy. Every time I think of him, which I do often because we work on similar areas, I am always amazed. So he is a former American astronaut who has been on 4 space shuttle mission. But just to get things started, just a phenomenal guy with amazing experiences and service to this country and to the society. He is also the executive director at the Electricity Industry Center at Carnegie Mellon University, where he's also a distinguished service professor at the Tepper School of Business and the Department of Engineering and Public Policy. He got his bachelor's degree from Harvard College and a PhD in experimental physics from MIT. His research and teaching interests are broad, but mostly focused on energy in the electricity industry, on technological innovation and change, on risk management, and management of technical enterprises, and obviously all of this under the umbrella of energy systems design. He received the Metcalfe Lifetime Achievement Award for significant contributions to engineering in 2002, and also received NASA's Distinguished Service Medal in 1977. It's a great pleasure, tremendous honor to introduce to you Jay Apt.
Thank you, Varun. Thanks a lot. I appreciate it. Great. Well, thanks. It's a pleasure being here. I lived in Texas for 15 years and was a HL&P customer before they became somebody else. I have many good friends who are here, and friends in Luminant and Reliant, TXU, and I have had the great pleasure to have some PhD students who came out of this program as undergraduates or master's degree. In fact, we have a current applicant from here at the moment to our program, and that's just a delight. So what Varun asked me to talk to you today about is some of the research that we've been doing on about a fifth of the area that the Carnegie Mellon Electricity Center works on renewables. And so hence the title. All right, so first some background on why people are interested in renewables. There is still in this country and largely in the world a very great interest in decarbonization of the electric power industry. And so let me give you a 60-year history of why people are interested in decarbonizing the electric power industry. This is the percentage of total U.S. carbon dioxide emissions that are from electric power. It's gone up. I was born in 1949. It's gone up from about 12% then to a little over 40% of total U.S. electric power emissions. Why? Because electric power is a greatly preferred way of transferring energy. Right? At the same time, the electric power system has not gotten terribly efficient in the use of CO2. It's gone down from about, 0.8 or so metric tons per megawatt hour back 60 years ago to not so much better than 0.55 at the moment now. Okay? And that's liable to go down here shortly. Why? Speak up. This is not a shy audience. I've been to Texas before. Speak up. Natural gas, exactly. That's right, which has about more or less 60% of the life cycle emissions that coal plants do. Okay. On the other hand, electric power generation in this country has not been static. It's been going up tremendously. There was little blips for various recessions. And although some people may not have thought that this one was so little, we're recovered largely from it at the moment. And it wasn't really as strong as the 1980 recession in terms of electric power, or even the one around 2000. Okay? But if you project this stuff linearly, you will see that we have to build about half the electric power system that we have now before 2030. Right? And that's even without electric vehicles. I've done quite a bit of work on EVs, and I'm not sure that EVs are going to come in the way that some proponents think. But if they do, that curve could go back to exponential. The thing to remember about that curve is that it was exponential until about 1973, at about 7.75% a year. Wow, if you had a business that was growing 7.75% a year, you're doing pretty well. Right? And it transitioned from exponential to linear after the 73 oil price shock. That was a profound difference. And we could see other qualitative differences in electric power. But basically, those are the reasons why people are interested in decarbonizing the system. Now, I'm here to tell you, having sat in on a bunch of state legislative discussions, that there are 3 groups that are required to pass a renewables standard in any state. The low carbon people, that is the Greens parties, the jobs people, and the energy independence people. You take out one of those 3 groups and your coalition fails to pass a renewable portfolio standard, right? And there's a lot of interesting stuff buried in that, but that's a different talk. Okay, so let me show you what the power generation looks like in this country, again, over the last 60 years. The blue is fossil fuels, the orange is nuclear, and the green is renewable. What? How can renewable have been that big? Well, most people don't think about one aspect. In Texas, there isn't much of it. What is it? Hydro. Yeah, right, exactly. Okay, so if you ask the question of what was the low carbon electric power, it was about 30% currently. Okay, renewables plus fossil. What's happened to the fossils is interesting. In fact, it's really interesting. The red line is petroleum. And back before the first oil embargo, we were on an exponential growth for petroleum as in everything else. In fact, coal was linear, everything else was exponential. And so we stopped that. We actually passed a law saying that you couldn't use natural gas for electric power generation, except under special circumstances. Natural gas has taken off again. And coal took all of the downturn during the recession. Okay? Every bit of it. That may have been because we knocked off doing third shifts, but in any case, that's what happened. All right, so here's a quiz for the students. No ringers in here. What percentage of U.S. power is now generated by renewables? 9%. That's about right, exactly, at 10%. Yeah. That's right. And it's interesting, if you don't show the earlier slides to people, most folks think a couple of percent and they're forgetting the hydro. And in fact, most state renewable portfolio standards do not count hydro, except for very small hydro in that. All right, so let's take a look at the electric power generation mix in 2010. 45% coal, smidgen of oil, mostly where? Hawaii and Puerto Rico. Yeah. Natural gas, about a quarter, nuclear, about 20%, and then various other things. And this is what the renewables breakdown looks like. The percentages are not this pie, they're the percentage of the previous pie, right? Okay. So just anchor on those percentages as we go through the rest of this. We also forget about municipal solid waste, and we forget about the black liquor boilers in the pulp and paper industry. Okay? Those are non-trivial. Okay? They eclipse certain other renewables. We're not going to talk about those today. All right, so let's talk about some wind farms. I picked this out of Ventec's Velocity Suite last week when I was putting the slides together for that. Those are the current wind farms, the ones over 5 megawatts or so. Texas has a lot, clearly. But the fastest growing isn't in Texas, it's actually in the Midwest. Okay, Texas is growing pretty well too. Wind production has been growing very nicely, right? Land use, which I think is going to be the limit to wind. It's not the electrical engineering. We'll talk about some electrical engineering stuff. Can be benign. This is a picture I took near a farm in Pennsylvania. The farmer gets between $3,000 and $5,000 a year rental for the turbines. This farmer is a happy camper. So land use can be benign or not so benign, right? These guys thought if a little weed killer was good, a lot must be a lot better, right? Okay. And land use requirements have been the subject of some not terribly rigorous work and needs to be done better. But in general, what you see is that this is in terms of acres per megawatt hour. Wind is a little worse than PV, solar photovoltaic. Both of them are quite a bit worse than traditional fuels. These count the surface mining in the case of coal and the other surface stuff in the case of natural gas. Hydro is pretty bad. You wouldn't know that in Texas, but it's got a lot of land use. Biomass is horrible, right? If you want to fire a plant with biomass that does a significant amount of electric power, good luck. Okay? In western Pennsylvania, we've got a 2,360 megawatt coal plant. If we wanted to biomass fire, that would have to be all of Pennsylvania for that one plant west of the Alleghenies. Trying to do that. All right, so let's talk about land use. Occasionally, some of you have been on YouTube and seen this, right? If you get on YouTube and Google wind turbine failures, you see fires and other kind of stuff. Stuff happens, right? It happens with gas plants, happens with coal plants, stuff happens. See it again afterwards if you want. But in general, the land use issues aren't stuff like this. They are because people are worried about the view shed. You can put up a wind farm on a farm, that's just fine, but you're not going to sell the farm for condos later. Okay. We've found for many years that putting wind near people is a much better wind in the best wind places in building transmission for a couple of reasons. I won't get into here. But what that means is if you put the wind on, let's say, ridges on the Allegheny Mountains in Pennsylvania, you are going to get into more land use conflicts than if you put it in McCamey, Texas. How many of you have been to McCamey? Yeah, okay. Good place to live? No, it's not a good place to live. It's windy, for starters. Right? And so you don't have those kind of conflicts. Yeah?
That last chart you showed had PV at 100 acres per megawatt hour.
Yeah, I think that's...
utility scale? Or
yeah, that's utility scale. But these are this guy's numbers. I think they're understated by about a factor of 2, but we haven't published on it, so anyway. Okay, so as I say, the wind, you may want to build near people, and there's a lot of work on that. All right, so now let's talk about some data. This is ERCOT, Electric Reliability Council of Texas, last year, and these are hourly data, steady, no? Yeah. And so this is the major issue that the electrical engineers have to deal with. Okay? And so here's the other issue. This is the load profile averaged over every hour in the year in ERCOT last year. And, you know, people come home and the peak power is at about 6 p.m. Okay? Minimum's about 5 in the morning. Not so much for the wind power, right? The wind blows about half again as strongly at night as it does during the day. The correlation is about minus 0.8. It's not completely anti-correlated, but you know, it's not great either. That's the other problem. And here's the third one. This happens to be for the mid-Atlantic states. the wind doesn't blow so strongly when you want to use the air conditioning. Okay. Now, those things were well known, and what I'm going to talk to you about in the next 20 minutes or so are some of the details of what we've found that will help people integrate wind, and I'll say something about solar, both PV and solar thermal. Okay, so here's the first piece. The statistics of wind are not nice bell-shaped curve normal distributions. They have some really weird features. And one of them is that the wind sometimes fails for many days. Here's Bonneville Power Authority in the Pacific Northwest in January of 2009. No wind for a couple of weeks, big high pressure area settled over it. When you talk to the guy who, Terry Oliver, who's their chief technology officer, he says none of our predictions ever looked at anything like this. Okay. Now they're lucky because they have a lot of hydro to buffer the wind. So let's take a look at wind on a finer time scale. This is 10-second resolution for a small wind farm. Big one looks about the same. This happens to be in ERCOT. And if you look at this and you say, well, that's pretty noisy data. From a mathematical standpoint, you can ask, is this noise white noise? How many of you heard the phrase white noise? Okay. How many of you know what it means? Okay, good. So what it means is the same amplitude at lots of different frequencies. So let's talk about that. If you pull out your eye thingy, you will find an equalizer on it, right? And you can boost the low notes over by the bass or the high notes by the piccolo over there. Okay, so what we're going to do is use a mathematical technique called Fourier transform. There's lots of other ways to do it as well, to ask what are the character of the low notes and the high notes. If wind or solar was white noise, every frequency would have the same amount of power in it. Okay, that would mean that you would need a lot of very fast ramping equipment to buffer the fluctuations of the wind. Batteries maybe, okay, certainly fast ramping gas plants. Okay, so we asked that question, and what we found was this. Here are the data for wind, and we find remarkably that it's not white noise. It is in fact much stronger by about a factor of 1,000 at the low frequencies, about a day, than it is at the high frequencies. That means that you can use very slow ramping plants, coal plants, slow ramping combined cycle natural gas plants to buffer the bulk of wind's fluctuation. Okay? And there's a remarkable character of this fluctuation. It's got a very well-defined frequency to the -5/3. That turns out to be a fairly deep feature of turbulence that was first predicted for wind, not wind output power, in 1941 by Kolmogorov. Many of you know statistics, know his work. And it wasn't confirmed for 20 years, and it wasn't observed in the atmosphere for about 30 years. Okay? And what this means is it's not white noise, and we've talked about those implications. That turns out to be really economically important if you're trying to integrate a very large amount of renewable power. Okay? All right. So we can learn a bunch of other things from the frequency character, they call it. The specialists call this the power spectrum. So you take a bunch of wind plants, these are the 20 largest wind plants in the Electric Reliability Council of Texas, and you look at those, and if you look at one of those wind plants, this is the power spectrum. Okay? And it falls off, it has the same character. At frequencies higher than about 24 hours, it falls off as this frequency to -5/3. So a lot of folks have written, including one of Varun's former colleagues at Stanford, that if you just cover the country with copper, connect every wind plant in the country together, it's all going to smooth right out. Okay, so we wanted to ask that question. And so here's what happens if you put 4 wind plants together. You get a bit of smoothing. That's good. Here's what happens if you put all 20 of those together. You get a bit more smoothing. That is to say, the ratio of high frequencies to low frequencies means that at the higher frequencies, when you add plants together, there's a bit more smoothing. Okay, that's good. But it also means this discussion has to take place on a time basis. When you say adding wind plants together smooths them, what you really mean is it doesn't smooth them much at 12 hours or 24 hours. It smooths them maybe by a factor of 10. Here is a factor of 10. This is a log-log scale. You know, about a factor of 10 between here and here at frequencies of a half hour or so. Okay. So let me, on the next slide, I'm going to take a cut through these data and look at the point of diminishing returns of when you connect these plants together. And so the top graph is what happens at 12 hours. First of all, you see that even if you connect all 20 wind plants together, you only get rid of about half the fluctuations at 12 hours. Second, you see, just looking at the top graph, after you connected about a half a dozen wind plants together, you're done. Okay, you don't get any more. And the next one is 6 hours, and the bottom one is an hour. So if you ask the question of how much of the fluctuations you take out at an hour, you take out about 95% of the fluctuations, okay, by connecting a few wind plants together. But remember the power spectrum, that is not a lot of the money that it takes to buffer wind, okay? It's some, but not a lot. Right, so we said, well, this is true in Texas. What about if we connect these big, large areas together? Maybe there's something special about Texas. We all know something special about Texas. But, right. So we looked at all these 3 areas where there's a lot of wind, 4 areas, and connected those together. And this is work that we just submitted for publication. And looked at the power spectrum of those, the low frequencies on the left, the high frequencies on the right. And they're offset in amplitude because they don't all have the same amount of wind. But basically, the character is the same. And you don't get very much more smoothing with even connecting all of them together. Let me show you this in a different way. Here's a graph. This is Bonneville Power, California, Texas, Midwest ISO, and all 4 of them together. And this is the slope. And what it says is there's a whole lot of year-to-year variability in the slope. There's more smoothing is down here, less smoothing is there. If you connect them all together, you don't get really any more smoothing. Okay? And that just says that the result that we found in Texas, if you connect about a half a dozen wind plants together, you're done. Means that you don't have to spend all this money on transmission lines. This transmission superhighway that people keep talking about is not justified on the basis of smoothing the wind. Okay? All right, so here's some data correlation coefficients. And fine, there's math in that. But it does, interconnecting does reduce the biggest, kind of anomalies. These 2 weeks without wind and so forth. This is a duration curve of just the last few hours, and the lowest curve, not quite the lowest curve, this, let me get this here, this curve here is the sum of all of them, and you see that it improves by about a factor of 2 over Bonneville and Texas, the step changes in an hour, okay? And that's a good thing. So you get some benefit, but it's not clear that it makes up for all the money you're going to put in the transmission. All right, so how much does it cost? We can do some fancy math and figure that out. I'll leave that as an exercise for the reader to read our papers. But basically, in ERCOT in 2010, what we found was 2 interesting things. First, this is in funny unit, dollars per megawatt hour. Divide by a factor of 10 and you get cents per kilowatt hour. About 0.8 of a cent per kilowatt hour is what it costs, based on the prices that we observe in ERCOT, to buffer this wind. Okay? But the prices dropped in 2009, and so it's down to 1/3 of a cent in 2009. They're back up a little. The other thing that we found was that the wind farms that are in a better area, have a higher capacity factor, have lower intermittency costs. It's quite interesting. All right, so let's ask a different question. Hydroelectric power is up and down. It has droughts. This is all of the hydroelectric power production in the U.S. In the early part of this graph, we're building more hydro. Then it gets stable, right? But there's one big drought and one small drought about every decade. Okay, don't need to remind people in Texas of droughts. So we asked the question, is that going to happen for wind? Okay? And so we don't have 40 years of wind data, but we have 40 years of data from airports. Now, these sensors are only about 10 meters up as opposed to a wind turbine that's 80 meters up, so there's little problems with it. But we asked the question, and we scaled it properly. And what we found was, yeah, the dotted blue line is the curve I just showed you from the last 40 years or so, and the green line is the estimate that we made from the airport data of all of the wind in the windy belt of the US put together. And it looks like, yeah, there's going to be some windy years and some not so windy years. So this was just kind of theoretical. What we see in Texas supports that. I'm going to introduce a measure called capacity factor. It's the percentage of the nameplate energy that's really produced by wind in a year. The capacity factor in Texas has varied considerably from 2008 to 2011, which is when we have a lot of wind in Texas, and it's down and it's up. So yeah, there may very well be some wind drought years and some wind good years, and people knowing that can cope with it a little better. Okay, so now let's talk about solar photovoltaic. This is where the big solar is, and notice this big solar state of New Jersey, not because it's sunny there, but because the last governor decided we ought to have some solar set-asides there. Okay, so there's a lot of sunlight. It's like 4,000 times as much solar energy deposited as we need. People get hung up about efficiency of solar cells. There is one place where efficiency matters, but it's not at utility scale. Okay, even at 7% efficiency, cadmium telluride cells, it would only cover 0.5% of US land, compared to like a quarter of the land for a crop. Efficiency is not a big deal, it's the money. The capacity factor stinks for solar, which means that you're not getting a lot of dollars out of your investment. Okay? But here's the big kicker. It's the capital cost. Unsubsidized cost in a place like Texas is about 25 cents per kilowatt hour. It's maybe 4 times what other power is, even other low carbon power. Okay. The price hasn't been decreasing all that much, despite what you read in the papers. And solar cells themselves, I could give the solar cells for free, right? And it would still be kind of double the cost of other low carbon power. Okay, so even though it's more expensive, it has to be better, right? Okay. So we looked at a plant which was then one of the biggest plants in the country in eastern Arizona. Here's a picture of the plant, and here's what it looks like in one day. Nice, sine or cosine squared. Sun goes up, sun goes down. Fine. This is the very next day. What's happening? Clouds. Yeah. You notice that their publicity picture even has clouds in it, right? Okay. Fine. So this is 1 minute data. This is 10-second data, right? And so if you ask the question, which is going to be more expensive to integrate, wind or solar, you can do the same kind of things in the low frequencies and high frequencies that we did. Right. Here's 2 years worth of data, so we can take that, and this is what we found. The gray is the wind, the red is the solar photovoltaic, and so there's much more power, about a factor of 10 more power at the high frequencies than there is for wind, which means it's going to require more fast ramping things that can go up and down quickly to buffer solar if solar ever becomes cheap enough to do at large scale than it does for wind. Okay, so what about solar thermal power, where you heat up a working fluid oil in a big tube? That should have some thermal inertia, so it should be a good deal less variable than solar photovoltaic that moves in and out. If a cloud comes over this thing, the fluid is still going to stay fairly hot. We finally got some data, and this has just been submitted to a journal. And again, in the frequency domain, here's what we find. Here's wind, red in this case. Here's the solar photovoltaic from 2 different solar photovoltaic farms. And here is the solar thermal. It is about a factor of 5 less variable at high frequencies than the wind, and maybe a factor of 50 less than the PV, just as you would expect. All right, so we can actually calculate the costs of those, and we've done that. And so the top line, don't worry too much about unless you're a specialist, that's the capacity factor. But the cost of variability, either in terms of dollars per megawatt hour, divide by a factor of 10, you get cents per kilowatt hour, so the first column is about 0.4 cents per kilowatt hour, or as a percentage of the total cost of power is over here. This column is for wind, this is solar thermal, and these are two different solar photovoltaic. Okay? So it looks like both the wind and the solar thermal are sort of half the cost of integration to counter that fluctuation than the solar photovoltaic. Okay? I'm going to get stricken from the Christmas card lists of the Solar PV Association. Okay. We do that. So we're an equal opportunity offender. We just do things the way they are. All right, so the last thing I want to talk about is what are some of the environmental costs of that variability. So a student who is now at Kima, who was at Brattle, and I looked at the NOx and CO2 emissions from gas turbines that are ramping up and down, okay, to do that. And so we built a toy system that was wind or solar plus N gas turbines, could be 20 gas turbines, to make pretty firm power. All right, so we actually got some data from a utility that was running both a big and small gas turbines. We had about 10 of these total. And we had the ramp rate and the amount of fuel that they're using, from which you can calculate the CO2, and the nitrous oxide emissions, which they're required to record for the EPA. And so we had data that showed when they're turning them off, data when they're ramping them down and ramping them back up. And what we found, for example, for a big turbine, a Siemens 501FD, was that the NOx emissions rate here was a function just of the power. It's optimized for high power steady state. Hey, if you're an engineer, that's what you would do. Why would you ramp these things? Well, now we know because there's a lot of wind. And if you're down here at low power, the NOx emissions are horrible, just awful, right? Okay, so we had a bunch of data of wind and photovoltaic, different resolutions. And what we did was, because we could take small slices of that where the wind was really blowing, so we got 95% wind in that time slice, or solar PV, we were able to look at the penetration of this all the way up to almost 100%. And so what I'm going to show you is what the specialists call emissions factor. And on this axis of what I'm going to show you is the amount of wind or solar in the system as a percentage, 0% up to 80 or 90%. And then this is the amount of nitrous oxide or carbon dioxide that's emitted. Okay? And what you would expect if you introduce 30% wind is that you'll knock off 30% of the emissions, right? That's what's called the displacement assumption. And nearly every state renewable portfolio standard makes that assumption. Okay? So we just asked the question. And what we found on the top here, this is a small turbine and this is a large turbine. They have two different ways of doing the nitrous oxide control, but on this side is the CO2. So let me focus on that for a second. This is like at 40% wind, this is what you expect and this is what you actually see. Okay? And that's because just like when I was learning to drive when I was 16, I put the gas to the floor, jackrabbit starts, and then I slammed on the brakes. My gas mileage was terrible. And you're seeing the same kind of thing for usage of these turbines. In addition, because you have to run some of them on standby, you've got some kind of idling emissions. For nitrous oxide control, it's very different. For this particular type of steam injection control, you don't see any benefit at all until you get to about 3/4 wind, and then it falls off. For this one, the one that I showed you that was optimized for the high power steady state, it goes down all right until you're about 15% wind, and that starts to get up. This work is now 4 years old, and we showed this to both Siemens and GE. And the result was GE kicked off a huge program to make a fast ramping turbine that didn't do this. And they announced last summer this flex turbine that they call it. It helps that the guy who's the head of the division is one of our graduates. Pay attention to it. So it is possible to do this. My message here, just before we finish up, is that the way that you're going to actually integrate these things is to get folks, not the folks who are manning the barricades saying, fill in the blank, renewable antimatter power is the wave of the future, and anybody who is against it is against mom and apple pie, which is the way that the trade organizations have acted. But rather to say, look, this stuff, like any other power generation technology, has problems. Nothing is a free lunch, but that doesn't mean you can't eat. All you got to do is understand what the characteristics of wind, solar, antimatter, if it ever comes in, are, so that then you can get ahead of the curve and learn how to integrate this stuff. Okay, so final comments. You can integrate this stuff. The amount of smoothing by interconnection is really dependent on the time scales involved, and that's something that hasn't been widely recognized. Covering the country with transmission lines is not justified from the standpoint of smoothing this stuff. There's going to be good and bad wind years, just like there are good and bad hydro years. Variability costs of solar thermal are about half of photovoltaic. At the moment, solar thermal is pretty expensive. Why? Because it doesn't work. The coatings are flaking off. They're having some problems. They'll get those fixed. Okay? I don't know if either PV or solar thermal is ever going to become affordable. But if it does, and if they were about comparable, your choice would be the solar thermal, just from the variability cost. Okay, so thank you, and I think we finished when Varun wanted to. So thanks a lot. And we've got 20 minutes for questions.
We have 20 minutes for questions.
Right.
A lot of time. So
Yeah.
questions. Students get preference.
That's the way I run my seminars. The first questions are always from a student so that the faculty doesn't dominate them.
Hi. So you looked at how pooling wind farms together reduces the variability.
Or not.
Or no,
Yeah,
well, to a
right.
certain point.
Yeah, that's right. The point of diminishing returns is about a half a dozen wind farms.
Yeah. Did
Yeah.
you look at that for solar? Because it seemed like on the
No,
very fine resolution.
we don't have enough data.
Okay.
I'd love to have those data, but we just don't have the data. The one thing I am looking at now, we've finally got data, but it's only for one of each, is to see if combining one solar plant and a wind plant help. But gee whiz, I mean, I'd love to have enough data to answer your question, but I don't have it. You're doing this because of the recording, right?
Yeah.
I can hear them fine. Okay.
Hi. Thanks for your wonderful presentation. And two small questions. One,
You know, any presentation sounds good if you give them chocolate chip cookies at the beginning, right? Okay, go ahead.
first question, what is the up-to-date methodology to predict wind production?
Okay.
And-
What's the wind weather prediction stuff? Is that what you mean?
Mm-hmm.
Yeah.
Yes.
It's really interesting. If you have time here, they make predictions out to 84 hours, down to an hour. And you look at the percentage error, okay, for a thing the size of ERCOT. My priors would be that this would go up like this. Actually, it doesn't. It goes up like this and rapidly saturates at about 15%. When I say rapidly, this is about, 6 hours or something like this. We are getting better. I should say we. People like AWS True Wind are getting better at wind power production. Inside of an hour, I'm going to talk dirty for a second, you can use a Markov model. It's just basically a persistent model. Outside of about an hour, that falls apart, and you need to know where the weather patterns are and so forth. We are getting better at that.
Okay. The second small question is, what is the ratio of balancing the variation of wind energy? What's the ratio between the wind energy, the gas energy we need, natural gas we need, to balance the variation of wind?
Okay, so if you were looking at the Bonneville Power Administration slide and said we didn't have any wind for 2 weeks, the answer would be you'd have to have enough balancing to fill in for all of the wind. Okay? In the Electric Reliability Council of Texas, wind falls off to zero about 7 days a year, if I remember the numbers right. So the answer is you need enough generation standing by there. And the problem is this. Suppose you're the proud owner of a natural gas generator, okay? And you're getting energy payments. That's great. Life is good. And then 10 or 11, whatever we have in ERCOT gigawatts of wind come in and undercut your energy payments because A, the wind has no marginal cost, and B, it's must run because you have to meet the obligations. Your energy payments get undercut. So you throw up your hands and say, I'm closing the doors, bye, I'm out of here. On the other hand, Electric Reliability Council of Texas has this reliability word in their title, right? And so they say, no, 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 don't go away. I'll give you a side payment to stay. And we're still working that out. We really are at the very early stages of that. But the answer is, I'm not speaking statistically correctly, but you may need 1-to-1. It's certainly not much less than that. Right.
Other questions?
So you talked about the work that you did with your student Katzenstein, I think it was.
Yeah, Warren. Right.
I'm curious where you model basically a set of wind plants with a set of gas turbines. One of the questions that's interesting to me is how that looks when you put that into a diverse, fully interconnected system that has varying demand and whatnot.
Sure. We tried to do that. We tried to there was a consulting firm that I will not name that has what they say is really the best model of that in the country, right? And so we said, well, great, we'll partner with you. Turns out their model had one coal plant, one gas plant, and a few other things. And so it really wasn't any good at predicting the ancillary services that you need. So we're not there yet. We're not there yet. And so it's, you're going to have to go to places like Excel and measure that. We are seeing coal plants that are getting ramped. And what we're doing now is we're looking at the continuous emissions monitoring system, the SEMS data, for those of you who are specialists, that the EPA requires. And we're taking SEMS data as wind penetration increases and sees what happens. My colleague Paulina Jaramillo is a student who's looking at that right now. Where'd the microphone go? I lost track.
Hi, my question is about how agnostic the numbers are for the variability costs. I mean, is it particular just to gas, or could it be applied to storage?
The numbers for the variability cost use the actual observed market numbers for the ancillary services in balancing areas like Texas. We can get them from all the organized markets: PJM, New York ISO, New England ISO, Texas, California ISO, Midwest ISO, and we use the actual observed market prices. Yeah, here's one.
Hi, I'm curious if you have any thoughts about energy storage technologies for the grid, and particularly whether you're talking about solar has, produces more power at high frequencies, and whether or not, if there might be more benefits to energy storage for solar.
Sure. Okay, so here, quiz time. What percentage of the electric power that we have in this country can we currently store? None, all right?
Well, pumped hydro.
About 2%, and it's all in pumped hydro, about 2%. 2-3%. It's not enough to really change the markets, okay? Going into the economics for just a second, the thing that makes electric markets really different from the markets for shoes or sweaters is that there's no inventory. And so the big effect, if we get widespread storage, is going to be a market effect, not so much a wind integration effect or a solar integration effect. The market effect is going to be profound, because it means that you don't have to have supply and demand match at any instant, which we have to now. And all of the markets are predicated on that, and all of the reliability is. Okay, so I'll come back to the question that you actually asked in a second, but first let me tell you a little bit about the storage technologies. There are people who are building new pumped hydro storage facilities that are not in the US, They're in Scandinavia, in Portugal, and in Spain. And I don't know about the Far East. I suspect there are too there. In non-traditional technologies, we have two things that are promising. One is thermal energy storage, molten salt, for example, phase change materials that you can use with solar thermal. And the second that I'm very excited about are some new battery technologies. I'm not talking about for cars, right? I'm talking about things with low energy density but also low cost. A lithium-ion battery that you can use in your Chevy Volt. Oh, I forgot, this is Texas. Everybody's going to be buying Teslas, right? Okay. So the lithium-ion battery that you use in your Tesla has a very high energy density. That's also got a very high cost. They're running about $10,000 a kilowatt hour for realistic numbers. What you want is something that costs the same as your lead-acid battery in your car, $150 a kilowatt hour. Problem with your lead-acid battery is that it has max 50 cycles before it dies, okay? 200 cycles if you get a really fancy one. What you need is 50,000 cycles, maybe a bit more. And so there are three companies that I know about, one of which is a spin-off from Carnegie Mellon University, so I know very well, called Aquion Energy. But there's basically three different technologies that I think have good prospect for a couple $100 a kilowatt hour, couple 100,000 cycle batteries soon. In fact, Aquion is building their first large-scale plant now. They're cutting metal for that plant, okay, and they've got small scale. So what's it going to do? Well, the first thing is if it comes in big quantities, it will change the market for these kind of what we call ancillary services that regulate the frequency to keep it right at 60 hertz. This is the stuff that I was saying we got the prices for. Those prices are enough to entice batteries to come into the market in certain places. Not where I live, but here, for example. And the second thing that it will do is change the markets. But the third thing that they may do is to make solar and wind much easier to integrate. But remember, there's not much fluctuation at the very high frequencies, the right-hand side of that power spectrum I showed you compared to the left side. So most of the variability is going to be taken out by slow ramping things. Batteries will have a role, but they won't be a transformative role. I'm sorry, Popular Science magazine, or Scientific American, their transformative role will be in the markets. Let's see, Aquion, I've forgotten the other two. I was just trying to remember them, but Aquion, and then there's two others that, for reasons because I probably got up at 4:30 in the morning, I can't remember right.
My question is about the demand side power spectrum. I've seen presentations like this, but I never see something that compares with the demand side power spectrum.
Actually, my very first paper, 2000 paper, where I showed the spectrum of this, I got some 14-second time resolution data from my local utility in Pittsburgh. It's amazingly similar to the wind. I have no idea why. And we've now got some other data, and it falls off the same way. I really cannot tell you a theoretical reason why it should be so close.
And then a question about penetration. So some of these issues really only matter as a function of penetration in a complex system. And so my understanding of ERCOT, for example, is that there aren't really any 0.2 instances where spinning reserves have been required as a function of the renewable generation side.
Ooh,
because it's a relatively small fraction. Even when it's hit the high fractions, it's like the incidents recently here in Texas in the winter loss and everything. You know, all the spinning reserve deployments have been.
Well, let's see. ERCOT, as I understand it, has changed the rules to try and procure both more 30-minute and more spinning, just because of the integration issues that they've got. Now, they're not spending a lot of money on it, but they have upped considerably the amount of 30-minute and spinning that they're procuring. Part of that has to do with the 2009 price or 2008 price spikes, but part of it is the wind integration, as I understand it. I'm not an ERCOT specialist.
Okay. Other questions?
I can do this all day. I love talking about this. I'm a geek with this stuff. I like it.
Okay, so one of your graphs, pertaining to smoothing of the power curves and also emissions associated with certain circumstances, I presume those that solar in that instance was utility scale solar. Do you think that distributed solar and perhaps distributed storage in the form of thousands and thousands of electric cars in a grid would change those characteristics?
Okay, so let me first talk about the rooftop solar, distributed solar. EPRI, the Electric Power Research Institute, has a really nice program now where they've got some monitors on a bunch of utility poles all around, and so we'll start to get some data. These data are scarce as hen's teeth. You just can't get them. The Million Solar Roof program out in California, you cannot get those data. But EPRI's trying to do that, and so we don't know yet. We don't know. Clearly there's going to be some correlation, but there may also be some smoothing. I'm an experimentalist. I don't theorize about this stuff until I see the data, right? Because you can really embarrass yourself that way. Ask me how I know that. All right, so now the storage. So let's go into a world where you have Teslas in every garage, or Chevy Volts, or BYD. BYD is not doing so well, but anyway, cars that have batteries in every garage. What's going to happen? Well, the first thing is that you can actually make some money in the regulation market, but not many people can do that. In all of California ISO, it's been known for 12 years now that 300,000 cars out of the 30 million in California are enough to provide all the regulation you need, right? So the first movers can make some money on regulation. And when my friend Terry Boston at PJM says, oh, electric cars are going to be wonderful, they're going to make a lot of money, that's what he's thinking about. We published a paper a year and a half ago or so that did the following. We took the lithium-ion batteries that are being used in cars into the laboratory, and we cycled them in two ways. One was what you would use for driving. We saw how they degraded. And the other was what you would use for driving plus grid storage. You buy low, 3 in the morning, you sell high at 3 in the afternoon, right? And so from that, because we know the cost of the batteries, and we did it parametrically, $10,000, $5,000, $2,000, $0 for the battery, we can get the degradation cost due to the additional arbitrage that you're doing. And we know how much you can make because the markets give us that. So we put these cars in 3 different markets. We put them in Philadelphia, okay, has a big swing day tonight. In Rochester, New York, different ISO, New York, and in Boston, okay, ISO New England. You make the grand total of about $50 a year on this if you're a car owner, even if you have 0 battery degradation. It's not going to be enough to float your boat. And so I'm pretty pessimistic that even an aggregator that gets all of our cars together is going to be able to incentivize all of us to use our cars that way. What I am optimistic about is that you may be able to modulate how you're charging the cars in order to help the grid. Let's suppose that all of us have cars plugged in and we live in McCamey, Texas, where there's a lot of wind. Now, the wind blows strongly, I charge all the cars if I'm the grid operator. The wind slacks off, I stop charging. I make a deal with you. I say, look, I'm going to have your car charged by 5:30 in the morning, but you let me decide when I'm going to charge. That kind of stuff, yeah, I believe in that. Yeah.
So you see a market?
Depends whether there's a market for electric cars. Here's why I'm a little pessimistic. If the car manufacturers deliver on their 50-ish miles a gallon that they've signed up to by 2030, is it? I've forgotten. I think 2030, 2035. If they deliver on that, that will be the equivalent efficiency, even with those lousy internal combustion engines, of what you can get with an electric car at probably lower cost. And so I'm a bit pessimistic about electric vehicles. In the near term, I'm pretty optimistic about them. I think you could buy an electric vehicle now and do good. And we published a paper in Environmental Science and Technology last year that looked, even with no change in the electric power system grid, all these dirty coal plants, you still make out good on pollution, with one exception I'll get to in a second, even in dirty places like where I live with electric cars. The one exception is sulfur dioxide. You increase that because you're burning more coal.
Couple more questions. I know there's one here and there, and then we'll stop.
Yeah, thanks. First, yeah, I thought the presentation was excellent. So your power spectrum analysis, you had the things you looked at, CSP, PV, and wind. So if you've done the same thing for, if you plotted coal or hydro or natural gas, right? And you mentioned plotting the load against the same thing.
Well, see, that's
would it
not
give you a perspective of how combining them would be total cost? Because the costs aren't zero for coal, right? Or integration of coal, I guess, per se, right?
Well,
just because we don't know the
kind
load.
of are. I mean, the coal plant ramps up and down to follow other sources, mostly load. Load can be predicted, I told you, wind's about 15%. Load can be predicted in a large area at about 4%, okay? And so the ramping to keep the frequency at exactly 60 hertz is done largely by the automatic gain controls on the big generators, the coal plants. There's a little bit of combined cycle gas that does that, but mostly it's the coal plants. And so the coal plants are responding rather than having real physical characteristics.
Right, so I guess that sort of gets to my question. How much of the quote-unquote cost of integration is due to how you and I use power versus the generation, the function of the generator itself? Whatever it is.
Active area of research. We're looking into that, and we don't know yet. I mean, the answer is there is some fluctuation in load. As I say, it's not all that high, but it's enough. What we also are looking into is whether you can use direct load control to help buffer wind, okay? And so we're getting data on how fast your air conditioner really responds when the utility commands it to go off, for example. Those data are also scarce as hen's teeth, so we're getting some of it.
Right.
We'll work on
Right,
that.
thanks. It seemed you just kind of showed which one has more inertia, essentially, right, on the ground.
Exactly.
Final question.
Not being from engineering at all, totally.
Neither am I. I'm a physicist.
Okay.
And I teach in a business school.
Okay. My question is about aesthetics and history, and I wonder if hydroelectric, if dams are inherently beautiful, or if we have just managed to create an aesthetic of dams, because I don't see people saying, "Ah, dam, how ugly." Whereas, personally, I think that wind generation is beautiful, and I see it on the French coast, and it integrates with cities, and people are like, "Wow." So, what does it take to make that happen? Number one, and number two, another small question that's probably a
Well, wait, let me answer that one first because I
Okay.
got a small memory. All right. So let me tell you about the history of large hydroelectric dams in this country. We were on an exponential curve. You saw that growing curve for hydroelectric dams until two things happened. One was Galen Rowell's unbelievably gorgeous photographs of Glen Canyon that was flooded by the Glen Canyon Dam. That book came out in '62 or '63. The second was the collapse of the Teton Dam, which was just about the same time, and a collapse with deaths of a very large dam in Italy. Okay. Those three nearly simultaneous events stopped the building of large hydroelectric dams in the U.S. There's still some building after that time in Canada. No state renewable portfolio standard that I'm aware of, I could be wrong, allows large hydro to compete. Okay, and that's because the environmental consequences are two. One is the flooding of the landscape, and the other is the fairly low on a life scale, but important early emissions from making the cement.
No, forget dams, thing of the past, but why can we not create an aesthetic of wind turbines?
Wind turbines have had an aesthetic. Many people think they are lovely, and the farmers do think they're lovely. There are a couple of things that, three things really, that have come up that will limit, or are limiting, the land use of wind turbines. The first is the viewshed issue. If you have moved to the Appalachians for nature, you don't want an industrial landscape in front of you. And so that's the key issue in many contentious wind, and that was an issue off Cape Cod for Cape winds. The second is the noise. They do go whoomp, 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 and they can be heard depending on the wind, downwind for 3 miles. And the third is in high latitudes, specifically Scotland, Britain in general. When the light is low in the winter, the sun's way down south, you get flickering that goes over miles and miles and miles as the sun is filtered through the blades. And those three are the main land use issues that have slowed down the adoption of wind. Okay. Probably running out of time. I'll get with you for your last one. Thank you very much.
This is good. I learned very much.